is Irishly, and for this video, I'm gonna discuss about geometry, but in real life. Meaning, I'm gonna give some real life situations that involves geometry. So what are you waiting for? Let's go!
Alright, so as I said earlier, we're gonna discuss about the topic geometry in real life. So this performance task is to be submitted by me, of course, and to be submitted to my math teacher, Teacher Jenny T. Taligatos. Alright, so our objectives is to learn how important geometry is in real life and to understand the concept of circles using real life situations. So in the next slide, we have here the table of contents. So for the first one, we have the parts of circle, geometry, and we're gonna apply geometry in astronomy, optics, and engineering. Okay. So here in this slide, we have the parts of the circle, and here are some pictures. Okay, so for the first one, we have here the radius or radii in plural. So this is a straight line drawn from the center. So the center or the center point of the circle to any point in its circumference. Okay, when I say circumference, like this one, it is the distance around the circle, or this ring right here, the ring of the circle. And also, radius, or once again radii in plural form, is half of the diameter. So here we have sector. Sector is a part of circle bounded by two radii. So we can see here two radii and an arc. So this is the first radius and another radius. So because it's two, it's called radii, and this is an arc here. So here is an arc. An arc is any taken part of the circumference, and there are different types of arc. First, there's a minor arc, and then major arc, and then semicircle. So later we will discuss those types of arc. Okay. And here we have also the segment. So a segment is a part of circle bounded by a chord. This here, a chord and an arc. So a chord is any straight line that does not pass through the center of the circle and its endpoints meets the circumference or touches the circumference of the circle. And a chord that passes through the center of the circle is what we call diameter. So again, a diameter is a chord that passes through the center of the circle. Okay, well here we have the tangent. So a tangent is we can say a line is tangent if it meets the circle at exactly one point. And that point where the line and the circle meets is what we call the point of tangency. And then here next we have secant. If the tangent only meets the circle at exactly one point, in secant it meets the circumference of circle in 2 points. So here, one here, and another one here. And lastly, we have here the quadrant. So a quadrant, it refers to a part of circle bounded by two radii, like this one here and another one here, that forms a 90 degrees. So this is a 90 degree or a right angle, and an arc right here, this arc here. Okay, so let's go to the next slide. So again, for the first one, we have geometry. So what is geometry? Geometry is a branch of mathematics that studies the shape of individual objects, their spatial relationships, and the properties of surrounding space. And it is one of the oldest branches of mathematics. And did you know that its name is derived from Greek terms geo, which means earth, and metron, which means measurement. So together, it means earth measurement. And eventually, it was realized that geometry need not to be limited to the study of flat surfaces, or what we call the plane geometry. Because there are two types of geometry. As I said, the plane geometry, that type studies about the square or the circle like that, or the lines. And the other type is the what we call solid geometry, which studies about the rigid three-dimensional objects like the cube and sphere and more. So now, let's go to the real-life situation in geometry. So the question is, if Maya sliced two pieces of cake, one with an angle of 38 degrees like this one, and another one with 67 degrees like this one. So now, what is the total degree of the two pieces together? So this two together, what is the measurement? And then also, what is the measurement of the major arc, or this one, the remaining pieces of the cake? So first, let me explain what a major arc is. It is an arc with a degree measure of more than 180 degrees, while a minor arc like this piece of cake here and also this is an arc with a measurement of less than 180 degrees. And another type of an arc is the semicircle, which is an arc with a measurement of exactly 180 degrees. So now, let's go to the solution. Okay, so this is the cake from the previous slide earlier. So let me use another figure for you guys to understand what I'm saying. So here we have circle P. It is called circle P because its center point is point P. So we name a circle according to its center point. So again here, circle P represents the cake, and this angle APB and angle CPB looks like the pieces of cake that Maya sliced. Okay. So for us to answer and to solve the question earlier, let's first learn what postulate 20 or arc addition postulate is. So here it states that the measure of an arc formed by two adjacent non-overlapping arcs like this arc AB and arc CB is the sum of the measures of the two arcs. Meaning, like here, we can get the measurement of arc ABC by adding the measurement of arc AB and arc BC. And here, just an additional information, this angle APB, this here, and angle CPB are the what we call central angles because their vertex lies on the center or the center point of the circle. And the measurement of an arc, of a minor arc, is always equal to the measurement of its corresponding arc. That's why arc AB, which is 38 degrees, is equal to the measurement of its corresponding central angle APB, which is also 38 degrees, and the same goes to this arc CB and angle CPB. Okay, so now let's find the measurement of arc ADC, or this major arc right here, and the measurement of arc ABC. So first, to find this measurement of arc ADC, we first need to find the measurement of arc ABC. So as I mentioned earlier, to solve it, we will just add the measurement of arc AB and arc BC, and their measurements are already given. So let's just substitute it. So arc AB is 38 degrees, says here, and arc BC or arc CB is 67 degrees. So together, if we will add it, it is equal to 105 degrees. So now, to solve this major arc ADC, we will just subtract the measurement that we got earlier to 360 degrees. So do you know why we will subtract it to 360 degrees? Well, it is because that is the measurement of a full circle or a whole circle. As you can see, if we will combine the measurement of arc ABC and this arc ADC, we can form a whole circle. So that is why. And then now, because we already got the value or this measurement of arc ABC, we will just substitute it and then bring down 360 degrees. So 360 degrees minus 105 degrees is 255 degrees. Therefore, the measurement of arc ADC is 255 degrees. And to check if your answer is correct, you can just simply add the 255 degrees to the measurement of arc ABC, which is 105 degrees. And then if the answer is 360 degrees, then your answer is correct. Okay. So next, here for the second one, we have astronomy. So what is astronomy? Well, spherical astronomy or positional astronomy is a branch of observational astronomy used to locate astronomical objects on the celestial sphere as seen at a particular date, time, and location on Earth, and it relies on the mathematical methods of spherical geometry and the measurements of astrometry. So spherical geometry right here is the study of geometric objects located on the surface of a sphere, like this in the picture. So next, we have here the real-life situation for astronomy. But first, let me discuss the parts of a sphere because it might be useful for our question or our situation later. So, the parts of the sphere includes the great circle, center, radius, diameter, and the two hemispheres. So, a great circle is defined as the intersection between the surface of a sphere and a plane containing the center of the sphere. Okay, so now, here is the question. If we split the Earth into two parts, so we all know the Earth is like in the shape of a sphere. So if we will split the Earth into two parts, we will be able to see the layers of the Earth. So here are the layers of the Earth, which is the crust, mantle, outer core, and inner core. So we can refer this view as the great circle of the Earth. So now, as I mentioned, it's a great circle. So I've drawn lines here. So these are some radii here and a chord. So here is the real question. So if the line segment JD is perpendicular to the line segment AC, and then AB here, the AB is equal to 2x plus 12 and CB is equal to 5x minus 3. Then find AB, CB, and AC. And just an information, this sign here or the symbol is read as is perpendicular to, as I said earlier. So this is read as line segment JD is perpendicular to line segment AC. So now let's find the value of AB, CB, and AC. But to find it, first let's solve for the value of the x. So here, we have here the AB and is equal to CB. So it is equal because here you can see this line JD. It bisects the chord AC. So when I say bisect, it means that it is a line that divides something into two equal parts. And this here, line segment JD is a perpendicular bisector. Perpendicular bisector because it you can see it bisects or it splits the line AC into two equal parts and in 90 degrees or right angle. So there. Earlier it says that the value of AB is 2x plus 12 and then the value of CB is 5x minus 3. So we will just substitute it and then here we will combine the like terms. So we move this 5x to the other side so that the 2x and 5x are together and the sign became negative because of the addition property of equality, and the same goes to this one. So negative 3 and the 12 will become negative, so negative 3 minus 12. Now we will just combine them. So 2x minus 5x is equal to negative 3x, and then negative 3 minus 12 is equal to negative 15. Now to solve this, we will divide negative 3 to both sides so that only x will remain in here in the left side. So negative 3x divided by negative 3 is of course x, and then negative 15 divided by negative 3 is 5. So the value of our x is 5. Okay, so now that we got the value of the x here, therefore, we will substitute the value that we got in this equation or in this expression here. So it became 2 times 5 plus 12. So 2 times 5 is 10. So we'll just bring down the 12 and 10 plus 12 is 22. And then also here in CB, so again substitute the value of the x in the 5x minus 3. So it will become 5 times 5 minus 3. So 5 times 5 is 25 minus 3 is also 22. So you can see the value of AB and CB is equals because as I said earlier, the line segment JD bisects this chord AC. So this proves that AB is equal to CB. So now the last one, we need to find the value of AC. So to find this, we will just combine these two, the AB and CB, because you can see they're connected. So it will become AB plus CB. So it will be 22 plus 22 because we will just substitute the values that we got. So 22 plus 22 is 44. So now we got the answer. So AB is equal to 22, CB is also equal to 22, and then AC is equal to 44. So next, for the number 3, or the third one, we have here optics. So optics or geometrical optics, or also called as ray optics, is a branch of optics in which the propagation of light is studied by representing light as rays. So here we have here the example or the question. Okay, so Taki is nearsighted. So her doctor advised her to wear an eyeglasses with a biconcave lens, like this in the picture. So as you can see, her eyes looks like the shape circle, and then we can say that the rays of her vision, the uncorrected and corrected, looks like angles. So let's use another figure for you guys to understand or to answer the question better. Okay, so if the angle of her uncorrected vision, this black angle here, is 22 degrees, and then if measurement of angle AMC is 35 degrees, so let me erase this angle EMD first, and I will show you what I'm saying. So here, you can see I draw two lines here connecting the point A to point M and connecting point C to point M. So this is the angle AMC, and its measurement is 35 degrees. Now, we will find the angle of her corrected vision, or this green angle here. So this green angle is an inscribed angle. It is because the vertex of this angle, point B, lies on the circumference of the circle, or on the ring of the circle. So now let me tell you the difference of an inscribed angle and a central angle. So an inscribed angle, as I said, its vertex lies on the circumference or the ring of the circle, and its sides are composed of two chords, like this line segment are AB, and then this is array because there's the other one has an endpoint, the other has arrow, means it is continuous. So here, the ray AB and ray CB. So the two sides of this angle is a chord. While this here, another one, the angle AMC, is an example of a central angle because its vertex lies on the center point of the circle, and its side consists of radii. So here, the radius MC and radius MA, so it is two radii. So that is the difference between an inscribed angle and a central angle. So now let's answer the question. What is the angle of her corrected vision? Okay. Solution. For us to solve this, we need to learn the Theorem 115. So it states here that the measure of an inscribed angle, this angle ABC, is equal to 1/2 the measure of its intercepted arc, which is here, its intercepted arc is arc AC. This one, and because the measurement of angle AMC, a central angle, is already stated, so I mentioned it earlier that the measurement of a minor arc or an arc is equal to its corresponding central angle. So it means that arc AC is also 35 degrees. Okay, so now let's solve for the measurement of angle ABC. So again, I said here it is already given. Measurement of angle AMC is 35 degrees. So here, the measurement of angle ABC according to the Theorem 115 is 1/2 of its corresponding arc, or the arc AC. And here, as said earlier, the arc AC is equal to 35 degrees. So let's substitute it to this one. So here, 35 degrees multiplied by 1 is 35 degrees. Divided by 2 is 17.5 degrees. Hence, the measurement of angle ABC, or this inscribed angle, is 17.5 degrees. Okay. So now we have the last topic where we will apply geometry is the engineering. Okay, so engineering. Of all the engineering disciplines, disciplines, of all the engineering disciplines, geometry is mostly used in civil engineering. So geometry involves the analysis and study of relationships among shapes, and civil engineers designs and assemble shapes to construct buildings, bridges, highway systems, tunnels, dams, and other structures. Engineers use descriptive geometry to visualize, analyze, and design structures and objects. And fractal geometry also helps them or the engineers to analyze various entities such as the porosity of soils, the clumping of materials, and the friction between objects. And all of this involve geometric patterns that repeat on a decreasing scale. And a thorough knowledge of geometry helps engineers and many other professionals to perform their job properly. Okay, so next, we have here the real life situation for engineering. So, the situation is, Engineer Elise built a house with arch-type windows like this one. So, we can see that the shape of the upper part of the window looks like a semicircle. Again, a semicircle is an arc with a measurement of 180 degrees. So, let me use another figure. So here, I made it into a circle and then copy the framings of the window as lines. Okay. So here we have the theorem 104, which says that if a radius is perpendicular to a chord, then it bisects the chord. So when I say perpendicular, it means that two lines intersects or meet at exactly 90 degrees. So here we can see that the radius MB is perpendicular to this chord AC. So we will prove that it bisects the chord. Okay, so here the given is this is circle M with radius MB, line segment MB, that is perpendicular to chord AC at point D. So this is the point of their intersection. So at the point D. Okay, so again, as I mentioned, we will prove that the line segment MB bisects line segment AC. So now, let's go to the next slide. And then we have here the solution. So, this one is the figure from the previous slide. And here is the statement that we need to prove. And this is the proof, and we have here the statement and reason. For the first one, it says, draw radii MA and MC. So the reason is 2 points determine exactly one line. And we can see that line segment MA and line segment MC determines exactly one line, which is the line segment AC. Okay. So next, line segment MA here and line segment MC. So line segment MA is congruent to line segment MC. And it is because the radii of a circle are congruent. Okay, next. For number 3, it says this one, line segment MD is congruent to line segment MD because of the reflexive property. So the reflexive property states that any shape is congruent to itself, and that a figure, this one here, this figure triangle AMC. So this figure is divided by a bisector, the line segment MB, into two equal parts, which is the triangle MDA and then the triangle MDC. So in short, this triangle AMC is divided into two equal triangles because of the bisector. Okay, so statement number 4. So angle MBA DA and angle MDC are right angles. And the reason is the definition of perpendicular. So when I say perpendicular, again, a perpendicular is when two lines meets or intersects at exactly 90 degrees. So as I mentioned, here the chord AC or the triangle AMC is divided by a perpendicular bisector MB. So that's why this two right angles MDA and right angle MDC are formed. Okay? Next, for number 5. So, triangle MDA here, MDA. And then triangle MDC are right triangles. And the reason is definition of right triangles. So, as you can see here, by connecting here the point A and point M in the the fourth statement. So by connecting the point A and point M of the angle MDA, we can already form this right triangle MDA. And the same goes to this one. By connecting point C to point M, we can of the angle MDC, we can already form the triangle MDC. And these two triangles here are called right triangles because one of its angles has a 90 degrees angle. So this one here, for triangle MDA, this angle in the letter D or the point D forms a 90 degrees. Well, for the triangle MDC, also here in the angle D, it also forms a 90 degrees. So these two triangles are right triangles. Okay, so number 6. So triangle MDA again is congruent to triangle MDC. So the reason is hypotenuse leg theorem. Okay, take note. We can only use this reason if we have a right triangle in our figure. So it is correct to use this one because we do have a right triangle, which is this two. Okay, so in hypotenuse leg theorem, it states that any two triangles like triangle MDA and triangle MDC that have a congruent hypotenuse and a corresponding congruent leg are congruent triangles. So we can see here that the hypotenuse of the triangle MDA here is the line segment AM, which is congruent to the hypotenuse of triangle MDC, which is the line segment MC. Okay, and both of these two triangles, triangle MDA and triangle MDC, have the same leg, which is the line segment MD. So, of course, line segment MD is congruent to line segment MD. And then, here, as I said, so, this is the hypotenuse for the triangle MDA, and here this is the hypotenuse for triangle MDC, and both of them has this leg. Now this this line segment AD is the base for the triangle MDA, and the base for triangle MDC is line segment CD. So there. Okay, once again, the parts of our right triangle here is the hypotenuse, leg, and then here, the base. Okay, so now it is correct that we use the hypotenuse leg theorem because as I explained earlier, the hypotenuse and the leg of these two triangles are congruent. Okay, number 7. Okay, line segment AB here is congruent to line segment CD. So the reason is CP-CTC. So when we say CP-CTC, this means congruent parts of congruent triangles are congruent. So the corresponding parts that are congruent, we have their 3 angles, 3 points, and 3 sides. So for this statement or this example, here we have triangle MDA again and triangle MDC. Let's use that as an example. So the 3 congruent angles here is here. We have angle A is congruent to angle C. Then next, angle M is congruent to angle M. Then angle D is congruent to angle D. Okay, for the 3 congruent points of these 2 triangles, first we have here point A is congruent to point C. Then point M is congruent to point M. Then point D is congruent to point D. Lastly, for the 3 sides, here, line segment MA of triangle MDA is congruent to line segment MC of triangle MDC. And it is also stated here in the statement number 2. Then next, line segment AD is congruent to line segment CD of the other triangle, which is already given here in our statement number 7. Okay, then lastly, line segment MD is congruent to line segment MD. And it is also written here in the statement number 3. And then now, finally, for the last proof, number 8. So, line segment MB bisects line segment AC. And this is the thing that we need to prove, right? So, here is the reason. A definition of bisector. Okay, so again, a bisector is a line that divides something into 2 equal parts. So, now here is the proof for this statement. Okay? So, next. Okay, now we have here the sources. For the pictures and the sound that I use for this video, and I would also like to credit SlidesGo for this beautiful PowerPoint template.
And that's all for today. Thank you for listening to my discussion. Have a great day. Goodbye!